Welcome back once again. Yesterday we discussed certain examples of ring along with its definitions, and we also came to know that a ring may or may not have identity element. When we say that identity, it is default to be understood that we are talking about multiplicative identity. And one more thing, we also noted that in case if identity is there in a ring, uh, it doesn't mean that every element possesses its inverse. Okay, and the elements which has inverse in it in R, where R is ring, then we say that particular element as unit. Okay. So these things we have discussed and certain examples also we have taken yesterday. And we have seen some examples where there was some there in some ring there were some units, and there were some examples where there was no identity. Okay. So this is a official definition. Of course, yesterday we have seen it, but for the sake of just a revision, I have just copied it from the textbook. So a ring is what? A ring R is a set with two binary operations. And when we say that a binary operation, it means closeness only. Okay, that is closedness only. So these binary operations are usually called addition, and we write it a plus b, and multiplication we write a times b or a dot b sometimes. Okay. And if A, B, C are such that they satisfy these following 6 properties, then we say that R is a ring. Okay, under these two operations. So first three, along with because these two, addition is a binary operation. So first four makes it R as a commutative group or abelian group under addition. And the rest two properties, if we say, because under multiplication also R is closed. So closedness and this fifth property, this makes R dot as a semi-group. And the third property is extra. This property includes both addition and multiplication as well. So here we see that left distribution and right distribution. Distribution of multiplication over addition from left. And the second one is a distribution of a multiplication over addition from right. So left distribution and right distribution both should hold. Okay. So if these 6 properties holds, then we say that R is a ring. Okay. Fine. So if you see, we have seen several examples. If we take suppose E, the set of even integers, and we consider E as a group, under addition, and let us take multiplication also. Is it a ring? Is it going to be a ring? Of course, sum of two even numbers is even. All right. Sum of two even numbers is even. And if 2 is there, then minus 2 is also going to be there. Similarly, if 2m is there, so negative 2m is also there. So additive inverse are there for every elements. Okay. And one more thing, what else we need? We need this property. So this also holds. All right. And this is abelian, of course, 2 plus 4 equals to 4 plus 2, something like this. Fine. And what about in additive identity? Additive identity is 0. Additive identity is 0 because 0 very much belongs to this set of this even integers. Okay, so E plus is going to be abelian group, as you know, and with dot it is a semi group. So this and distributive, of course, holds. So this is going to be a ring. So can you tell me what are the units, or before that E has in identity or what? Any identity? Is identity is there in E? When we say identity, it means we are talking about multiplicative identity. Hello.
Yes.
This will contain the elements of this form. So we cannot have any element to m into uh, any element of this form, so that you are multiplying to other elements like this. So it is going to give us the same element like this. Okay. So you can't get this kind of element here, because this is certainly going to be 4 times m into n. And of course, in a ring, we have not talked about anything cancellation and all kind of thing. Okay. So there is no identity. Usually identity is going to be one only in this case, in when we are taking integers or real numbers. Okay. So if there is no identity, we cannot say anything about inverse, okay, or unit element. Okay. So let us see another example. Example number 7. If there are n number of rings, R1, R2, Rn, we can use to these to construct another ring. So this is called direct product. In fact, in group theory, we don't have this direct product in the last semester. Okay, but anyway, you can direct sum. I am sorry, direct sum. Okay, but thing is that they are just when we are writing like this, it means we are putting one element here from here. So there are n rings. So they are going to collect. So this sum is going to give us a collection of n tuples. Okay, where ai belongs to ri. So a1 belongs to ring r1, a2 belongs to ring r2, a3 belongs to ring r3, like this. And then addition is defined as component-wise addition, and multiplication is defined as component-wise multiplication. A1 times B1, A2 times B2. So A1 times B1 is the first element, and A2 times B2 is second element. Similarly, A1 times Bn is going to be another element. Okay, in this for this element when we are taking their product. Okay, this is called ring. The ring is called direct sum of R1, R2, R3, and Rn. And interesting thing is that don't pre-assume that R1, R2, R3 are going to be a subset of some particular ring kind of thing. Okay, they can be any, or you can take this R1 to be E. You can take this as a integers, something like this. You can take this as a real number. Okay, so these kind of things, or you can take other any other example what we have taken yesterday, or you can take z cross z. Yesterday we have seen these examples. Okay, so they can be anything. So of course they are numbers. They are using numbers. You can use other rings also where there is no number, but there are some symbols. Okay, so that we will see. Okay, so naturally, this is R plus is a group which is abelian, and product is commutative, of course, because A, B, sorry, yeah, R plus is going to be abelian. That we need to be, it need to be checked. Okay, directly we cannot say because we don't know about R1, R2, R3. Fine, this is from R1, this is going to be from R2. So we cannot say anything as of now. Fine. So this is a ring. Okay, let us see something more. There is another example. Of course, yesterday we talked about Z cross Z. Okay, so these are, I think, you will be, you can note these examples. They are good examples, in fact. Uh, Similarly, we can talk about R cross R, okay, with the usual addition and multiplication. Okay, and also we can talk about the set of complex numbers under addition and multiplication. We can also talk about Q Z cross Q under addition and multiplication. We can also talk about Q times R under usual addition and multiplication. And we can also talk about Z cross Q cross R, these products. So when we are talking about this, I'm telling this, this is the usual addition and multiplication. So addition is component wise addition and multiplication is component wise multiplication. Okay, here. So there also we can have addition and multiplication. You know the component wise, how we can component wise multiplication. So if there are two elements x, y, and then we have x1 and y1, then their sum is going to be x plus x1 and y plus y1, some like this. Okay, and their product xy and then times x1 y1, their product is going to be x x1 and y y1. So this you should remember. On tuples we have this kind of structure, this kind of definition on of addition and multiplication. Similarly, you can define it this define addition and multiplication on this product also. Fine. Just to see what we have used here. This will be applicable on these also. Fine. Okay. So let us see one more some more examples before proceeding further. Consider the example of n cross n matrices over the set of real numbers under matrix, usual matrix addition and multiplication. Okay, is also a ring that you can verify. But for certain cases, let us see if n equals to 1, then m1r m1r this is equals to what? All 1 by 1 matrices. This is equals to nothing but real numbers.
R.
Okay. Yeah, real number. Okay. So you know that r plus dot is a ring. Huh? So there is nothing to discuss about it more. So if n is greater than or equals to 2, then there may be so many cases. Okay. So let us consider n equals to 2. Then what we have? M2 over the set of real numbers. And this is going to be a collection of all those matrices A, B, C, D, such that A, B, C, and D, they belongs to the set of real numbers. Okay. So M2R, and reuse matrix addition and a multiplication is a ring. This you can verify. Of course, you know that M2 plus R, sorry, M2R, you know that M2R plus, this is abelian group. Under addition, I'm talking about. This is abelian group, okay? And matrix multiplication is associative, you know. So this is a semi-group. This is semi-group. Okay. All right. Rest you can you can just remember these examples. they may be useful. But the thing is that why I have quoted this example. Uh, can you tell something about whether this M2R plus dot is commutative or not?
No, sir.
No, sir.
No, sir.
No. Why?
Matrix
So because
multiplication is not
M2R dot is not commutative.
Yeah, very good. So because M2R is uh, dot, no? Yeah, dot is not commutative. When I'm writing like this, it means matrix multiplication is not commutative, huh? Or matrix multiplication uh, in general not commutative. Okay. Some more examples, let us see, and then we can interesting examples. Gaussian integers.
सर
Yes.
सर इसका इनवर्स तो सर वो तभी एग्जिस्ट करेगा सर जब जीरो मैट्रिक्स रिमूव कर देंगे.
Yeah. Yes. So that's why we didn't talk about unit and identity. When we require a ring, so we need to see only two things with respect to multiplication. First thing is should be closed. So product of 2 cross 2 matrices is again a 2 cross 2 matrix. All right. And second is associative. Matrix multiplication is associative always. Fine. Hello.
Yes.
So
Yes,
as
sir.
of now, we are not saying anything about inverse or unit. You, of course, you can try it out. You can think of uh, whether there is any unity, identity. So of course, you are going to get identity, huh? Fine. Identity will be what? 1 0 0 1.
0 1.
0, 1.
Yeah, this is going to be identity, huh? And all non-zero, I mean non-singular matrices in M2R are going to have their inverse. Fine. So all non-singular matrices in M2R are going to be unit. All right. Hello.
Yes, sir.
Yeah. So that is the thing. So it has identity also. It has units also. But the thing is that you need to specify that the unit, what are the unit? Units are all those 2 cross 2 matrices with non-zero determinant. Okay. So let us see Gaussian integers. This also we have seen in group theory. Okay. So let us define Zi. One more thing, I am just for the sake of clarification. Sometimes you people used to write like this for a set of integers. This is wrong. If you are using Z as variable, so you can use like this. All right. But you are when you are denoting Z as integer, you need to write like this. Like this. When you are using set of real number, you have to write like this. If you are using set of complex number to denote, then you have to write like this. So they are universally accepted notations. You cannot write set of integers in this form. Okay.
Okay, sir.
Similarly for natural number also. So Zi, this is a collection of all those elements of this form A plus IB such that A and B belongs to set of integers. Okay. Uh, let us write the set the set Zi is called called set of Gaussian integer. Gaussian integers. Okay. Of course, you know that there are infinitely many number of elements, so its order as a group is going to be infinity. Huh? Fine. The number of elements when we talk about Z plus Z, sorry, Zi is a ring. Zi is a ring. So for that you need to verify first. What you need to verify? You need to verify that Zi under addition, and addition is component wise addition. Okay, is an abelian group. It's an abelian group, and addition is defined like this: a plus ib, and then c plus id. They are going to equals to. This is going to be equal to a plus c I times b plus d. Okay. So since a and c are integers, so their sum is going to be an integer. So we can write a prime or a dash, and then here also we can suppose this is b dash. So like we can write like this: a b, a dash, and b dash. They are also in integer. Okay. So this is a closed. You know that from the definition it is clear. Okay. And the rest thing you can find it out. What is the inverse? What is the additive identity and all? Fine. So and associativity under addition. Second thing, बाकी सारी चीजें आप प्रूफ कर सकते हैं, ठीक है ना? मैं I'm not going to prove it. You have read in understood it in group theory. Second thing is that Z under multiplication is a semi-group. Is a semi-group. So for semi-group, what we need to do? We need to see that whether it is closed or not. Okay. So for closeness, let us define multiplication a plus ib. This is one element, and second element is a plus cd. So usual multiplication of complex number, what we will be having: a times c minus bd, and plus I times what we can write BC and plus AD. A, C, B, D all are integers, so their product and differences and sum, they are going to be integer. So this belongs to where? This belongs to Zi. So this is closed. And then you can also verify the associativity. You can verify the associativity. Okay. So this is how we can see that Zi is a ring. Let us be more specific. What we have taken here, Zi, and we are taking a and b from the set of integers. We can change this Z to another with another set. We can replace it. So another is that Gaussian integers modulo n. Modulo n. Then if we define it, now we are not going to write like this. Okay. We are not going to write it like this. Well, I'm going to write like this. Okay. Zn I. This is equals to the collection of all those elements of the form a plus bi, where a and b belongs to Zn. Fine. Then you know everything. Everything will be parallel to that one. That the last example we have discussed. And one more thing, the addition here we are going to use will be under modulo n. Okay, so when we will be writing a plus ib, this is general addition. Okay, and then we will be writing like this. Fine, c plus id. So this is going to be equals to a and plus c modulo n and plus I times b plus d modulo n, like this. Okay. Similarly, in a product a plus ib times c plus id, this is going to be equals to ac minus bd. Okay. So this product, their product is going to be under modulo n. Okay, or should I write like this? A multiplication modulo n c. Okay, then minus what you are going to write b multiplication modulo n bd bd. Okay, plus I times we are going to write what B.Sc, B multiplication C modulo n, and then what else we have here? A multiply modulo n with D. Yeah, with D. Okay. So this is what we are going to use for this. All right. Similarly, we can, in particular, in particular, if n equals to 3, then z3i, this is going to equals to a plus ib, where ab belongs to z3. Okay. So in z3, we know that elements are 0, 1, 2. So how many elements is are going to be in this? I think 8 elements. In Z3i. These A and B having choices from Z3. So you can take everything 0. So you will be getting 0 here. You can take A is 1 and rest thing is 0. That is B is 0. So you will be getting 1. And then 2 also you will be getting. Okay. You fix 1 and then you change B. You fix A with 0 and then you change B. Okay, like this. Or you fix B, you can change A, like this. Okay. So similarly, you will be getting I and then 2I, then 1 plus I, and 2 plus I, 1 plus 2I, and 2 plus 2I. I guess the 8 elements. 1, 2, 3, 4, 5, 6, 7. No, 9. Yeah, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, 9 elements. So actually, cardinality of this Zi, or we can say the order of this, is going to be 3 square. This equals to 9. And in general, Zn I, order of this as a group is going to be what?
N square.
N square. Good. So this is going to be N square. What about if when we took Zi?
Not
Infinity.
defined.
Infinity. So many. Huh? Okay. Uh, infinity. This will be countable infinity. Okay. Let us see some properties of ring. So there are some properties in theorem 2.1. We have rules for multiplication, and here we have 6 properties. Okay, so let us see one by one. First, we have to prove that a0 equals to 0, a equals to 0. Okay, so we can start a. We can write a0 plus 0 like this, and this we can write a, and 0 we can write 0 plus 0 because additive identity is there, and then 0. And in the right hand side, using distributive law, a0 plus a0 plus 0. Okay, a0 plus a0 plus 0. This implies here in the left hand side we have a0 plus 0. So we have cancellation law because R plus is an abelian group. So in a group, cancellation law holds both cancellation law, right and left cancellation law. So we can use left cancellation law because we want to prove that a0 equals to 0. So a0 equals to 0 we can prove. Okay, so from here we have we can cancel these two. We can left cancellation. So in the left side we have 0, and in the right side we have a0 plus 0. And you know, when we add 0 element, it is going to be, by its property, give us a0 only. Fine. So this implies that 0 equals to a0. Similarly, 0a you can we can talk about 0 plus 0a. Okay, and then we can write 0 plus 0 plus 0 and a, and this is equals to 0 plus 0a and 0a. So using right cancellation law, or we can write 0 plus 0a equals to 0 plus 0a plus 0a, and the right cancellation law because this is a group under addition. So in the left hand side we have 0, in the right hand side we have 0 plus 0a, and 0 plus 0 is nothing but 0a. Okay, so we proved this the first property. Okay, the second property, a times negative b equals to negative times of a times b. Okay, equals to negative times of ab. So this we can see the second property. We know that b, and if b is any element of ring, so b plus minus b is going to be equals to 0. Okay, or we can write like this. Let us b minus b or b plus b, like this. You know, this is a 0. Okay, this implies that what, b plus minus b equals to 0. So let us multiply on both sides by a from left. So b plus minus b, this is equals to what? This is equals to a times 0, and a times 0 is 0. Just now we have seen in the first part. So using distributive law, we can write ab, okay, ab plus a times negative times of b. This is equals to 0. Fine. So this gives us what? A minus b is equals to minus times of ab. Fine. So we proved this part. I think of these two we have proved. Okay. So now we can prove, once we prove this equals to this, then we are done. Okay. So for this, what we can do? Here we have a negative a. Here we have negative b. So we can write. Consider a plus minus a is equals to 0. Okay, so you need to see what we need to prove. B is coming in the right side, so we need to multiply here by b from right. So a plus minus b, and just operate b from right. So b 0b 0b is equals to going to be 0. here we have AB plus minus times of A and B. This is equals to 0, and this implies that minus AB minus AB. This is equals to minus A times B. So this proves the second part. They are very seems to be very easy, but little tricky in while proving. So next part, minus times of A minus times of B equals to AB. So this we use, of course, we use often, but thing is that when it comes to prove this, sometimes it is become difficult. Okay, let us see third part. So we need to prove that A minus B equals to AB. This is the need to be proved. Okay. So consider left hand side negative A, negative B, and let us write it minus A times C, where C equals to minus times of B. Okay. So this is equals to from here we can write AC like this. Okay, we can use we can write AC like this. Okay, fine. And then we have a minus times A, and then minus times of this C is nothing but minus B. C is nothing but minus B. But from the 2, what we have? We have a minus times AB like this. Okay, and then minus times of minus times, and this is going to be AB. Okay, like this. Next, we have fourth part. This is about distribution, left and right distribution over subtraction. In one sense, we can say when we write minus B, it means we are talking about the additive inverse of B. So there is nothing like a subtraction and all, but thing is that just for the sake of your understanding, I use this word. Okay. So in fact, we are going to talk about distribution of multiplication from left and right over sum of some element and additive inverse of another element. Thing is that. Okay. So let us see fourth part. AB minus C. This is going to be equals to AB minus AC. Like this. This we need to prove. Okay. So let us consider B plus minus C. Okay. B plus minus C, and then let us multiply from left. So this is equals to this equals to AB, and then plus A minus times C. Okay. So this is equals to AB plus what we can write here using the second property minus AC. So this is done, and then another part also we can do. We can consider BC and A from right. So we have a B. Okay, we can write B plus minus C and A from right, and this is equals to BA and plus minus times of C and A and BA, and from the second property we have C times A, right? So this proves the fourth part. And now fifth part is that if furthermore, if R has a unity element, not unit element, R has a unity element. Okay, of course, later on we will prove that unity in a ring is unique, just like we have proved in group theory. The identity in a group is unique. Okay, so here we can also prove. But until now, because we have not proved it, so that's why a word is used here. Has a unit. Okay. Later on, we will say that the unity, not unit. Unit is the element, are the elements. Units are the elements of a ring which has multiplicative inverse. Okay. So if 1 belongs to R, a unit T in R, okay, in R. So what they are telling that 1 time 1a, I think, negative 1a equals to minus a. So we need to prove minus 1a equals to minus a. I think we can prove, huh? You know, just we have seen minus b times a equals to minus ab. All right. So this you can replace b. Suppose you can take b equals to 1, the identity element. So this implies that minus 1 times a equals to minus 1b, and property of the identity is what? 1b is nothing but b. So this is going to be b, like this. Okay. So because b is arbitrary, you can prove that you can replace b by a, or else you can use another pair of this result for that. Okay. So there is no problem. Just a minute. All right, and then we have a hello. Hello.
Yes, sir.
Okay.
Sir,
One more part is there. Minus. They are asking to prove that minus 1 and minus 1 is equals to 1. I think using the result, use what you are going to use. You are going to use negative a, negative b equals to ab, like this. Okay. So just replace a equals to 1 equals to b in it. Okay. And you can get the result. Fine. This may be the last thing I'm discussing today. Uniqueness of unity and inverses. So I'm leaving it to you. You can, because you know that they are talking about unity and inverses if they exist. If a unit has a unity, that is identity, it is unique. So you know that in a group, you have proved in a group when you were sorry, in a group unity, or in other sense we say that identity is unique always, and inverse of some particular element is unique. Fine. So that you can prove. This is very similar to that of group. Okay. So you can try it out. Same proof will work here. Do yourself. Okay. So with this, let us conclude discussion for today.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.